Our next speaker is going to be Chaojian Li, also from Rice. And in this sort of theme of the last talk was about making useful models smaller so that they can work on resource constrained hardware, for example. And Chaojian's talk is going to be about how you can adapt models on hardware that are also resource constrained and maybe in new environments. So please take it away.
Yes, thank you. Yeah. Hello, everyone. I'm Chaojian from Rice University, and I'm glad to present our proposed hardware-aware learning to optimize. It has been accepted by CCV this year. And when we're talking about the motivation of this work, we have to come to the success of machine learning algorithms that has brought an explosive demand for embedded machine learning powered intelligence into IoT devices. For practical deployment, many of them require on-device training or adaptation for enabling them to continuously learn from new data and adapt to new environments, which is ongoing demand. Without adaptation, just as shown in the figure below, we can say the machine learning model may not be able to keep a high accuracy in the new environment, which are different from the collected dataset before, and some serious problem may be caused by such directly deployment without adaptation. However, the realization of on-device continuous model adaptation remains a bottleneck challenge because powerful performance of machine learning algorithms often comes at a prohibitive training cost, while IoT devices are often extremely resource constrained. Based on this driving motivation, in contrast to standard training, on-device training or adaptation needs to solve the following challenges. Challenge one is that there are various models and deployment environments. So how to deal with such various models and environments with a general design? In other words, an automatic optimizer with one-for-all feature is highly desired. That means I only have one optimizer, but I want to deal with all the models and all the environments. And the challenge two is how to achieve faster model convergence and high accuracy, given that limited data is available or can be stored in IoT devices. And the challenge three is how to implement it with much boosted training energy or time efficiency for possibly wide adoption. For adaptation, we can use two kinds of optimizers, but both the two kinds failed to meet the challenges mentioned above. One is traditional handcrafted optimizer like SGD or Adam, but they require heavy and manual hyperparameter tuning, which cannot solve challenge 1 and challenge 2 at the same time. In other words, they can only achieve fast adaptation and high accuracy with tuning for a spatial model and environment. Otherwise, it cannot perform well in various models and environments. Another kind is mental optimizers. Unlike the traditional handcrafted optimizer with a manual design mapping from gradients to updates, mental optimizers use a neural network for such mapping. Their input is the gradient from optimize, that is the machine learning models to be optimized during adaptation. And their output is the update for those optimized. With such a knowable design, they have better generalization ability than the traditional optimizers. In other words, they have the one-for-all feature. They can work with various models and environments without tuning. However, one big issue is that they are often more costly due to the mental algorithm's own overhead, which makes the challenge 3, implementation with boosted training energy or time efficiency, a more serious problem in this case. To this end, we propose Hello, hardware-aware learning to optimize, a practical mental optimizer dedicated to resource-efficient on-device adaptation. Compared with the previous optimizers mentioned above, our proposed Hello has a one-for-all feature, one optimizer for all optimizees, which is for challenge 1. And Hello is faster and better added with an innovative Jacobi Regularizer, which is for challenge 2. Finally, thanks to the proposed structure sparsity regularization, Hello is more hardware efficient, which is for change 3. Then I will give more details about them. As a mental optimizer, Hello has a one-for-all generation capability, which makes it could work with different models and environment without tuning. In this way, the change 1 on how to deal with various models and environment could be solved. To solve change 2 about how to achieve faster model convergence and high accuracy, we propose a powerful regularizer called Jacobi Regularizer, which encourages the optimized landscape to be smoother and flattened. Intuitively, such a landscape helps Hello to explore faster and more widely in a neighborhood, which makes it favor our goal of faster and better. And some past works have showed that constraining the Jacobi helps on training the autoencoders or increase the classification margins of neural networks, and therefore enhances the model stability. While they use Jacobi regularizers in traditional handcrafted optimizers, we are the first to extend this line of idea into learning to optimize or mental optimizers field, and all results demonstrate its effectiveness in improving the accuracy in addition to faster convergence speed, which I will cover later. Besides the Jacobi regularizer mentioned just now, we also introduced another regularizer, structure sparsity regularizer, which enhances the energy efficiency from a second angle, enforcing the structure sparsity on node updates. In other words, the outputs of Hello at each iteration, such that the prior iteration complexity and hence resource cost could be slimmed down. Especially for each layer I in the optimi, we set it to have the probability Pi to be updated by Hello at each iteration. So not all layers will be updated each iteration, and the layers updated in this iteration may not be updated in the next iteration. And the traditional optimizers without a knowable design cannot take advantage of such stochastic structure sparsity, thus perform worse than Hello, even with great search the structure sparsity hyperparameter during the adaptation. So to summarize, our Hello optimizer features the following highlights. First, the one-for-all feature, one optimizer for all optimize. Second, the faster and better convergence thanks to the Jacobi regularizer. Third, being more hardware efficient by structure sparsity regularizer. This solved the three changes caused by the mismatch between prohibitive training cost and limited on-device resource mentioned before. To evaluate our proposed Hello, 5 datasets include MNIST, CIFAR10, and 3 IoT-based datasets, 6 different optimize, 4 metrics, and 2 platforms are considered in the experiments. In other words, we not only take the training loss and the test accuracy in consideration, but also report the energy and running time measured in SOTA IoT hardware. And when comparing with 6 baseline optimizers, including 4 traditional handcrafted optimizers and 2 mental optimizers, Hello could bring higher accuracy with up to 16% less energy cost. And each component in Hello plays an important part in the boosted performance mentioned above. From the Ablation study in the Two Legalizers, we can find the vanilla Hello without the Two Legalizers cannot surpass Eden, the SOTA handcrafted optimizer. And after adding Jacobi Regularizer, Hello could achieve better test accuracy after convergence, which matches Jacobi Regularizer score faster and better. And Hello with both the regularizers leads to lower training loss and higher test accuracy while having smaller variance in the same energy bucket as compared to all baselines, which proves that the two regularizers integrated into Hello need to not only faster adaptation with reduced energy cost, but also offers a bonus benefit of improving convergence stability. To summarize, we propose Hello, hardware-aware learning to optimize, a practical mental optimizer dedicated to resource-efficient on-device adaptation. Hello as a mental optimizer, not only being able to have the one-for-all feature, one optimizer for all optimize, but also achieve faster and better adaptation via Jacobi Regularizer and more hardware efficient via the structure sparsity regularizer. And the experiments in the SOTA IoT hardware and various datasets and optimize shows that Hello could achieve higher test or adaptation accuracy with up to 16% less energy cost. Thank you. That's all for the presentation on Hello.
All right, thank you, Chaojian.
Thank you.
We have a few minutes for questions, so let's see if we get any coming in. Meanwhile, while we wait, I have one question that maybe I didn't catch it if you mentioned this, but is any of the work here related to the idea of optimizing across devices? Or is this all considered purely local, purely on device with no expected communication between devices or central servers?
Okay, I got your idea. In fact, I think we are the first to use the mental optimizers into the IoT devices because no one have tried to solve the on-device adaptation from the optimizer aspect. That is, the optimizer is how to update your models, and they just copy the optimizers from server trainings. That means those trainings are not targeted for IoT devices, but for for hardware with more energy buckets. And although there are some works, for example, the two mental optimizers I listed here, they are just try to demonstrate that their mental optimizers could have the same performance with the handcrafted, but they didn't find a good applications for those mental optimizers. So in our works, we are the first to combine the advantage of the mental optimizers and also add some modifications to make it could run in IoT devices. So I think to answer your questions, I think we are the first to solve the on-device adaptation from the optimizer aspect to make it more energy efficient. Yeah.
So this may you may have answered this next question, but a question we got is, what is the cost comparison between this and other regularizers?
I just want to confirm. You mean the metrics? We compare ours and the baselines. If this is a question, and I think I listed the four metrics here, we compare the training nodes and the test and the adaptation accuracy, and also the energy and the running time. But here I only cover the adaptation accuracy and energy in the figure I showed in this in these slides. That is, we collect the energy to train such we collected the energy to train such optimize in the specific data set in a specific hardware, and we collect other energy and plot its curve together with the average training loss and the test accuracy. Yeah, I'm not sure if I answered your question.
Well, hopefully that answered their question. That was a question I was relaying for someone else. Very interesting. Thank you very much.
Thank you.
And we'll now move to our next speaker. Thank you,